Vectors are going to be a very important concept as you move through informatics and data science, as vectors are going to be how we represent all of our data going into machine learning algorithms or data mining, for example. In our module, we're going to use vectors to represent text documents. And so what we're going to have are word vectors. And so words will, essentially what we're going to do is we're going to take a document, we're going to define a vocabulary, and the vocabulary consists of all the unique words that we're interested in modeling, and then a word is going to be represented by what is known as a one-hot vector. That is, every dimension in our vector, every element of our vector, is going to correspond to a particular word in our vocabulary. And so this one-hot vector is going to be 1 at the index location corresponding to that word and 0 everywhere else. So here's an example with the words east and north. So in this case, we have a vocabulary of 2 words, east and north, so our dimensional space is 2. And so we're going to have east correspond to our 0th element and north correspond to our 1st element. And so the word east is 1, 0, and the word north is 0, 1. So then we take any text or corpus and we're going to represent it as a linear combination of the one-hot vectors in our vocabulary. So a linear combination is just a sum of scaled vectors. So consider the following 2 sentences: east, east, north, east. So that's going to consist of, we have 3 easts, which are 1, 0, and 1 north, which is 0, 1. And so we're going to take our 1, 0 vector, multiply by 3, and add it to 1 times our north vector, giving us a new vector, 3, 1. So our sentence east, east, northeast is represented by the vector 3, 1. Okay, in the second sentence, northeast, each word occurs once, so we have 1 times our east vector, 1, 0, plus 1 times our north vector, 0, 1, giving us the vector 1, 1. So here is what these 2 vectors, these 2 sentences look like in our 2-dimensional vector space. So our first sentence, east, east, northeast, is coming over here in x in east 3 and 1 in north. And our second sentence, northeast, comes over 1 in x or east and up 1 in y or north. And notice when we're defining these vectors, the order of the words doesn't matter, just their counts. Okay, now let's do this with a more complex, more realistic text. And this is, we're going to use radiology text. So we're going to take this sentence: small rounded hypodensities are seen within the right kidney, possibly representing simple cysts but not fully characterized on this non-contrast study. Okay, so we need to take 2 steps. We need to determine the vocabulary, and then we need to create a mapping between the vocabulary and the vector space. So let's step through this. So first off, determining the vocabulary. The vocabulary are the unique words in the document that we're interested in. So we're going to use a package called TextBlob to get the words for us, and then we're going to use a NumPy array to represent the word vector. So we can create a TextBlob object by creating an instance of a TextBlob, and we're going to pass to it the text that we're interested in. In this case, let me make sure I run that. I'm going to take my radiology sentence and convert it to lowercase, and then I have this object blob. Well, blob has various attributes, one of which are the words that it found. So here we have small, rounded, hypodensity. You can contrast words with tokens. So tokens include things like the punctuation. So we have our terminating sentence here, and let's see, our right kidney, and then you see we have the comma right here. So you notice that the words, we've successfully peeled them away from the punctuations, and so we don't have to worry about that as we've done with our simpler text processing examples. Okay, so I now have the words in my document that I'm going to create my vocabulary from. But what I want are the unique words, so I can use a set to do that. And so if I look at, first off, I can print the length of UWords, and we can look at UWords. I wanted to print the length. Oops. So we have 21 words in our original document. Oh, I keep forgetting to do length. 21 words, so these were all unique in this document. So these are the words that our vocabulary is going to be built from. So now I need to create, well, I think I lied before when I said we were going to use a NumPy array. Well, our vocabulary is going to be represented by a dictionary. So the key of the dictionary is going to be a particular word in our vocabulary. And then the value is going to be an index from 0 to 20, in this case for our 21-word vocabulary. And so that's going to correspond to an element, a location in our vector. And I'm creating this dictionary by zipping together the words and this range of numbers. So I'm going to have a word 0, a word 1, a word 2, and so on. And then this becomes our word map, which we can look at. So the word but is our 0th element in our vector. The word R is our 6th element, and so on. And so our last word is kidney in the 20th element. So what's the dimensionality of our space? 21. And so now we need now that we have this vocabulary, we need to create a vector representation of sentences. So here I have a new sentence: tiny calcific density is seen within the right kidney, possibly representing small stone versus vascular calcification. And so what I need to do is I'm going to convert it to lowercase, because that's how I have my vocabulary defined. I'm going to create a word vector, which is going to be a NumPy array of dimension 21. And then for every word in my sentence, I'm going to take my word map dictionary and find the index that corresponds to that word, and I'm going to add 1 to my vector at that location. And so that's going to be this count of how many times that word occurred in my sentence. Now, if I have a word that's in my sentence that is not in my vocabulary, I have to ignore it. And so that's why I have this try except. So if I try to get the index for a word that's not in our vocabulary, we'll get a key error. And so I'm just going to skip over that with a pass statement. So here is what this sentence 1 looks like as a word vector. So I got 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, 1, 1, 1. Okay, now let's take a second sentence. Nonspecific interstitial opacity seen at the right base with evidence of bronchiectasis and small blebs. These likely represent post-inflammatory changes. Now you see that there's a lot of words here that are not in our vocabulary. And so they will not be part of our vectors representation of this document. So again, I create a text blob object by passing in a lowercase version of my sentence. I create a new word vector, which is a NumPy array of zeros. Again, the dimensionality is 21. That's the dimensionality of our vocabulary, independent of how many words are in the sentence that we're looking at. And then I go through every word in my sentence. I try to get the index of that word in our vocabulary, and then I will add 1 to that vector. And so here is our vector representation of sentence 2. And you see that we have 1, 2, 3, 4 non-zero values within this 21 dimensional space. So all these words that were not in our vocabulary are not contributing to our vector representation. Okay, here's a third sentence. Tiny calcifications are seen within the liver, likely representing a sequel of prior granulomatose infection. Same steps. I need to get the words out, so I create a text blob instance by passing in a lowercase version of my sentence. I create a 21 element NumPy array of zeros. I loop through every word in my sentence. I try to get the index of that word in our vocabulary, and I'll add 1 to that location in our word vec 3. And so here you see is the vector representation of sentence 3 based on the vocabulary that we previously defined. So what we want to know is which of these sentences, documents, is most similar to each other. And so we're going to use this cosine similarity. So we have a vector representation of each sentence, and what we want to compute is this angle alpha. Now the closer that angle is to 0, the more similar, the more parallel these two vectors are. So our mathematics are that the cosine of the angle is equal to the dot product of the two vectors divided by the norm of the two vectors. And so here I've written a cosine similarity function, and what it's going to return is the angle. So to get the angle from the cosine, we take the arc cosine, and there's a NumPy function for that, arc cosine. So, and there's also a NumPy dot product function. So I take the dot product of the two vectors v1 and v2, and then I divide by the norm of v1 and the norm of v2 and return the arc cosine of that. Now this angle is reported in radians. So the cosine similarity of word vec 1 with word vec 2 has a value of 0.79. Word vec 1 to word vec 3 has a value of 0.886. And if we take the word vector cosine similarity to itself, we have a number that's approximately 0. So vector 1, so sentence 1 is most similar to vector 2 and least similar to vector 3. So that is an application that we will be playing with in this module, is to use vectors to represent text and then do vector manipulation to get an estimate of similarity between the various texts that we are exploring.